So here's another test for maxima and minima, the second derivative test. If you have a critical value and the second derivative is greater than 0 there, then that value is a local minimum. If the second derivative is less than 0 there, then it's a maximum. So we have the first derivative is greater than 0 if x is not equal to 2. So that's telling me it's greater than 0 everywhere except at x equals 2, which tells me it's probably equal to 0 there. The second derivative is greater than 0 if x is less than 2. So that's telling me that it's concave up to the left of 2. The second derivative is less than 0 if x is greater than 2. So that's telling me it's concave down to the right of 2. It has an inflection point at 2, 5, which shouldn't surprise us because we know that it changed concavity at x equals 2. The limit as x approaches infinity is 8, so that means it has a horizontal asymptote at y equals 8 to the right. And the limit as x approaches negative infinity of f of x is 0, which tells us it has a horizontal asymptote at the x-axis as we go to the left. So I think it's easiest to start with the end behavior and then fill in the gaps. You know, like tails for the end behavior. So we know that the right hand of the side of the graph is going to be going off to 8, and the left hand side of the graph at some point, and these are estimates where you would start, is going to be skimming along the x-axis as you go to the left. Then you want to fill in between. So you're given that point 2, 5. You want to draw that point, and you know that to the left of 2, 5 it's concave up, and to the right of 2, 5 it's concave down. And since that first derivative was greater than 0, it is going to be increasing everywhere. So you're not going to have a max or min that's going to turn around. So that was important to note. So that when you join these tails that you drew initially, you know that it's concave up here and concave down here. You don't need to worry about it ever changing directions and having a local max or min. Here's another example where you're given the graph of the derivative and you need to sketch the graph eventually by finding all these characteristics of the graph. So because this graph is the first derivative, you need to remember that it's not the graph itself. So what can you tell from the first derivative? You can tell where the function's increasing by where the first derivative's above the x-axis, and the interval where it's decreasing by seeing where it's below the x-axis. You can see local max or mins by seeing where the first derivative is crossing the x-axis so that it's changing direction on either side of a critical number. You can tell where it's concave up or concave down because remember that the second derivative tells you when it's concave up when it's greater than 0, and since the second derivative is the derivative of the first derivative, that means that where my first derivative is increasing, my second derivative has to be greater than 0. And where my first derivative is decreasing, my second derivative is going to be less than 0. Then we'd put all these together to find the graph. So f prime is positive between 1 and 6, and again from 8 to infinity. So that's where f is increasing. F prime is negative from 0 to 1 and 6 to 8. So that's where f is decreasing. Critical numbers of f occur at the zeros of f prime. So that's at 1, 6, and 8. And since f prime is going from negative to positive at 1, x equals 1 is a local minimum. Since it's going from positive to negative at 6, x equals 6 is where the local maximum occurs. And since it's going from negative to positive at 8, x equals 8 is another local minimum of f. So we've answered A and B. Now let's look at C. On what intervals is f concave upward? Well, remember, f prime is increasing where f double prime is positive. So since f prime is increasing from 0 to 2, f double prime is positive from 0 to 2, so f is concave up there. Likewise, f prime's increasing from 3 to 5, so f double prime is positive there, and f is concave up there. And then the same for 7 to infinity. Likewise, f prime's decreasing on from 2 to 3 and from 5 to 7. So f is concave down on those intervals. And then the inflection points occur at the endpoints of these intervals. So at 2, 3, 5, and 7, it's changing between concave up and concave down. So then they're giving you a point of f of 0 equals 0, so they're giving you just one point to start with, and then it's supposed to sketch the graph of f. It's helpful to mark off along the x-axis the places where it's going to be increasing. The function will be increasing and decreasing. Also, plotting max and min values. So you know the x values of where they occur, but you don't know the y values. So the y values are up to you. So here's a min at x equals 1, a max when x is 6, and a min at x when x is 8. Then you want to add the inflection points, and you want to mark off where it's concave up and concave down. And it's going to be changing concavity on either side of those inflection points. So you'll know that your graph turns around at the minimum here, and it just changes curvature at the max as you pass through that inflection point to concave down, and changes curvature here again to concave up. And notice that it's increasing though from here to here. So you're going from the min to the max. You're not changing direction, you're just changing curvature. And that can be not nice to draw, as you'll see in my drawing. And then you're going to turn around at the max, and then you change concavity from concave down to concave up at this point, all the way down to the min, and then increasing again. The inflection points are the ones that are kind of tricky to draw smoothly. So in this example, the inflection points are not that subtle, but sometimes they can be hard to draw. So if you're doing it by hand, you might want to, let's say on a test, you might want to point out where the inflection point is, or that it's changing concavity there if it looks very subtle.